Hello everyone, welcome to lecture 23. So today we are going to talk about equilibrium of rigid bodies. So we also at some places we also call it statics of rigid bodies. So we have done dynamics till now. Now we're going to talk about statics of rigid bodies or equilibrium of rigid bodies. Okay. So what do you mean by, let's say, equilibrium of a particle? So this is something we are familiar from our school, isn't it? So we all know about the Newton's second law for a particle. So I'll just write it here. Mass times acceleration of the particle relative to inertial frame is equal to net external force, right, on the particle. Now, if the particle has to be in equilibrium, then the external force must be equal to 0, which implies that acceleration of the particle related to inertial frame is 0, which further implies that the velocity of the particle related to inertial frame is constant over time, right? You see, this also means that we can always find an inertial frame such that the velocity of the particle will be 0 in that frame. Okay, so let me just write this down. This also means we can always find an inertial frame in which Vpi is equal to 0, right? So basically the body or the point, the particle will look like it is in static condition. It's not moving. So that's for a particle. What can we say about rigid bodies? So what about rigid bodies then? Can we simply say that if the net external force on the rigid body is 0, then this implies equilibrium? Well, it turns out that's not the case. If we want to take an analogy from the particles, we said that the particle has to be such that its acceleration is 0. Now, a rigid body is comprised of several particles. So, for rigid body, acceleration of all particles should be 0. Okay, let's see what does this really mean. Should be 0 for equilibrium. All right. Now, using rigid body kinematics, acceleration of any particle p in the rigid body. So suppose this is a rigid body. Here is the center C, center of mass, and any arbitrary particle p. So acceleration of p related to I is equal to acceleration of c related to I plus omega of the rigid body related to I cross product omega of the rigid body related to I cross small r of p related to c, right, plus alpha of the rigid body is related to I cross product small r of p related to c. Okay, so if the acceleration of every particle has to be zero, then from this formula, because this has to hold for every p, or actually small r of p slash c, isn't it? Now you can see, if r p slash c is 0, then we simply get ap slash I is equal to ac slash I, and this has to be also be equal to 0 because it has to hold for every particle. So definitely this is 0. Furthermore, since it is for every small r, you can also show that omega has to be 0 and alpha has to be also equal to 0. Okay, so this simply means acceleration of c related to I is equal to omega of rigid body related to I is equal to alpha, and that's equal to 0. All three has to be equal to 0. And you see, what does this really mean about the velocity of any particle? So Vp slash I, again using rigid body kinematics, is Vc slash I plus omega of the rigid body cross product Rp slash C, isn't it? But again, as omega is 0, this implies Vp slash I is equal to Vc slash I. So velocity of all the particles are the same. Of all particles in a rigid body are same during equilibrium. Well, then just as for the particle, this again means we can always find an inertial frame in which velocity of any particle of the rigid body is 0, right? Such that velocity of any particle of the rigid body is 0. So the rigid body basically is in statics in that inertial frame. Okay. Alright, let's see what is the implication of AC slash IE being equal to 0, this being equal to 0, and this being equal to 0. What does this really imply? So using the linear momentum balance for rigid body, you can recall mass times acceleration of C slash I is equal to net external force on the rigid body. And since AC slash I is 0, this implies net external force is equal to 0, right? So this is from L and B. Now let us see what do we get from A and B. So A and B, if you can recall, this simply means the inertia tensor related to C into alpha of the rigid body related to I plus omega of the rigid body related to I cross product the inertia tensor C into omega of rigid body related to I, right? This is equal to net external moment about the center of mass C, correct? Now you see, because of equilibrium, alpha is 0, omega is also 0. So this implies M external is also equal to 0. So you see, equilibrium of rigid body implies that force external is equal to 0 and moment external about the center of mass is also 0. You see, this also implies that moment external about any other point is also 0. Because when you transfer the force from one point to the other, you get an extra term in moment, right? So let me just write it down again. So here's a rigid body. If at C you have F external and M external, then at any other point P you have the same F external, but the M external changes to M external plus R P slash C cross product F external. Actually, it is R C slash P. So you can recall it from the force moment equivalent system, right? Now, if M external about C is 0, if M external about C is equal to 0, this implies M external about P, which is equal to M external about C plus RC slash P cross product F external, right? But this is 0, this is also 0, so this is also 0. So basically, equilibrium implies that net external force on the rigid body is 0 and net external moment on the rigid body about any point is also 0. But is that sufficient for equilibrium? You see, the equilibrium of rigid body, so this implies that F external is equal to M external about any point is equal to 0. But does this also imply, is the other way also works? That F external equal to M external about A equal to 0, then does this imply equilibrium? Well, it turns out that's not the case. You need something more. Why is that not the case? Because you see, if F external is equal to 0, this only implies acceleration of C related to I is equal to 0, right, from LMB. But M external equal to 0 about C, that simply implies the inertia tensor about C into alpha of the rigid body plus omega of the rigid body cross product omega, cross product I omega so this is equal to 0. But this itself, this does not imply that alpha and omega are also 0. Only the product is 0, but individually that's not the case. It does not imply. Okay, so that's what I meant, that the reverse does not hold. So what extra condition do we need? So you see, we figured out earlier that if alpha and omega are 0, then velocity of every particle of the rigid body is constant, and then you can also think of an inertial frame in which the velocity of every particle is actually 0, right? So in that inertial frame, so in the spatial inertial frame, the kinetic energy K of the rigid body will then be 0, isn't it? Because velocity of every particle is 0. And actually in any inertial frame, Vp slash I is equal to constant, right? But in the spatial inertial frame, since Vpi is equal to 0, so kinetic energy is 0. But then you can remember work energy theorem for rigid body, according to which the kinetic energy of rigid body, the time derivative, that's equal to F external on the rigid body dot product velocity of the center of mass of the rigid body, right, plus M external of the rigid body related to C dot product omega of the rigid body, right? But because F external and M external are 0, this implies that K dot is 0. So this means kinetic energy of the rigid body at any time t is equal to kinetic energy of the rigid body at t equal to 0, right? And which means it's also equal to 0 in the spatial inertial frame. Okay. Now see, what does this mean if kinetic energy is 0? Does this mean that velocity of every particle is also 0? So it does mean so. You see, if we write down kinetic energy for a rigid body, you can decompose into translational and rotational kinetic energy. So this is half m vc slash I magnitude square plus half ic omega dot with omega, isn't it? But this rotational term, if you write down ic in the coordinate system of principal axis, then IC becomes diagonal, isn't it? And omega will have three components, omega 1, omega 2, omega 3. And then this becomes half I11C omega 1 square plus half I22C omega 2 square plus half I33C omega 3 square. Okay? And the first one is simply half m vc magnitude square. So this is equal to 0. But because m is greater than 0 and each of the I are also greater than 0, and the sum is also equal to 0, this simply implies Vc magnitude is equal to omega rigid body magnitude is equal to 0. Okay, which implies that kinetic energy of the rigid body, sorry, kinetic energy was already 0. So this implies the rigid body is actually in statics, right? Vp slash I is equal to 0 for all the points. So it is an equilibrium, right? So what we have finally found out is that for equilibrium, the necessary thing is number one, net external force should be 0. Number two, net external moment about center of mass, let's say, is equal to 0. And number three, the body is in equilibrium at t equal to 0. See, the last condition is just to ensure that velocity of every particle at t equal to 0 is equal to 0. Okay, so if these three conditions hold, see, these two hold for all time. So this should hold for all time. And third one, if this holds at t equal to 0, then this implies equilibrium at any time t. Isn't it? Because you see, because of third condition here, the velocity of every particle is 0 and kinetic energy is 0 at t equal to 0. But then due to 1 and 2, the rate of change of kinetic energy is also equal to 0. So kinetic energy at any time has to be equal to kinetic energy at t equal to 0. Now since kinetic energy is at t equal to 0 is 0, so kinetic energy at any time is also equal to 0. So velocities and omegas are also 0 at any time t, and so the body is in equilibrium at any time t. Very simple, isn't it? So basically these three conditions together imply equilibrium at any time t. Alright? The equilibrium condition for a rigid body essentially gives us 6 equations. So you can recall, we just said that net external force is equal to 0 and net external moment about any point is equal to 0. Now, since each of them are vector equations, so we have 3 plus 3 equal to 6 equations in total. Okay, so in general we'll have 6 equations. Well, it can turn out that in special cases we will have less than 6 independent equations. So let me give you an example. So suppose here is a rigid body which is clamped okay, so you can see the body is clamped on one end and then we are subjecting it to some force P at the other end. And we want to know what are the reaction from the clamp support. Okay, So if I draw the free body diagram for the rigid body, so we remove the support and replace it with the force that is provided by the support. So we have this force P, the reaction big R from the support, and also the moment big M from the support, isn't it? About a point, let's say C here, which could be the center of the support area. So here's the rigid body having reaction R, the reaction moment M, and the applied force P, which is known. And our goal would be to find out what is the reaction R and the reaction moment M, so that the body is in equilibrium, statics. So we will use the two equations ever. So first is F external equal to 0. So this implies big R plus big P is equal to 0, which implies that big R is equal to minus big P. Right? Very simple. And you can see there are three equations for the three components of the reaction force, Rx, Ry, Rz. Okay? So three equations for Rx, Ry, and Rz. Similarly, when we do moment external about C equal to 0, then because R is passing through C, it does not generate any moment. So we'll have M plus position vector of P with respect to C cross product the force P, right? And this is equal to 0. So from here we also get the reaction moment. So you can see how we can use the equilibrium condition to find out the reaction from the support. But I must also warn you that we cannot always get the reaction from the supports. Just think of another condition. So we have the same clamp beam. Okay. But also under a support at some other point, and then there's a force acting here, P. So when you draw a free body diagram, it has the reaction force R, then the reaction moment M, then you have the reaction from the other support, and you see it's a point contact, so it can have reaction in all three directions, Fx, Fy, Fz. And then you also have the applied force P. So how many unknowns are present here? So unknowns are M, R, and F. Total 9 unknowns, right? Each of them has 3 components. But we have only 6 equations. We can say that net external force is equal to 0 or net external moment is equal to 0. Right? So this is also called a statically indeterminate problem. Statically indeterminate problem. Basically, just using the equations of statics, you cannot solve for all the reactions. So that's why we call it statically indeterminate. So just using equations of statics, we are unable to obtain all the reactions. All right. You might wonder, why do we have only 6 equations? if we have used these two equations, right? Each of them are 3. Why don't we also say that we can get an extra equation by saying that moment external about some other point P is equal to 0. So this actually does not give you any extra equation. So I can write that here. This does not give extra equation. You can at most do moment balance about only one point. And once you have done it, then moment balance about any other point will be automatically satisfied. Alright? So we can have at most 6 equations only. So let us now see some special cases when you can have in fact less than 6 equations. So of course the general case, we have 6 equations, right? Then suppose there is a case when all the forces are concurrent, okay? When all the forces on the body are concurrent, which means they are passing through the same point. So maybe here's one force, then there's another force, another force, another force. See, they when extended, they all pass through the same point. So you have F1, F2, F3, and likewise. So you see, in this case, of course, we have one condition that net Fi is equal to 0. So this gives you 3 equations. But when you do moment balance about the concurrent point, which we say it is P, so net moment balance about P is automatically satisfied. Isn't it? Because you see all the forces are passing through P. So moment balance about P is automatically satisfied. So this does not give you any extra equation. So in this case, we have only 3 independent equations. So we have only 3 independent equations. Okay. Then we can have a condition when the forces are all collinear. Okay, suppose the forces are all actually coplanar. So they are all in the same plane. So this could be, so suppose this is the plane, and there's one force, F1, F2, F3, and likewise, but they are all in the same plane. Suppose the normal is K, K is the normal, so this implies Fi dot K is equal to 0. So they have no out of plane components. So you can see when you do net force balance, then in the K direction, we automatically get force equal to 0, right? So this is at most just 2 equations. We have only 2 equations here. Similarly, when we do moment balance, let's say about any point P in this plane, So when you find out moment due to all the forces about the point P in the plane, you only get moment in the k direction. Moment in the I and j direction are automatically zero. So moment balance about P equal to 0 gives only one non-trivial equation. Okay, so that means in total we have only three equations independent. Okay, likewise we can think of several other special cases where we can have forces and moments acting, but the equations of statics are not all independent. We have less than 6 independent equations. Let's now do some example. So think of the coplanar system. So suppose we have a beam which is clamped at one end and also on a roller support at the other end. Okay, and then it is subjected to coplanar forces P, Q, and then there is a couple also at point C, okay, of magnitude say m, and the endpoints are A and B. And then our goal is to find out the reactions from the support. Find the reactions from the support. You see, because it's a coplanar system, all the forces are in the plane of the paper, and the moment that is acting is out of the plane of the paper. See, the forces has to be in the same plane, but the moment should be out of the plane of the paper. Then we call it a coplanar system. So we just read that it can give at most three equations. And let's see how many unknowns are there from reaction. So from here, because it's a point contact and it's a planar problem, so it has at most two reaction components, isn't it? If you say it is x and that's y, then we have ax and ay present here. And over here, we have only by, because it's a roller support, bx is automatically 0, right, due to roller. So we have three unknowns. Ax, ay, and by. Okay, and also three equations. Correct. So therefore, this is also statically determinate problem. All right, statically determinate problem. Okay, let's do another example now. So suppose we have again a beam which is clamped at one end and on roller support at another point. Okay, and there is a force acting, it's a Q here, and also a end moment M. So can we find all the reactions in this case? So say this is point A, this is point B. So at point A, what are the reactions? Because it's a clamped end. See this end, it cannot rotate, right? So since it cannot rotate, you can recall from the previous class that there will be a reaction moment, isn't it? And also because it cannot displace in either x or y direction. So we have ax, ay, and also the moment, right? Na. Then from here, since it's a roller support, so it only can give by. There is no ax, isn't it? And also it does not provide any moment because it's a point contact. But you see, there are total 4 unknowns now. But only 3 equations because it's a coplanar system, right? So therefore we say it's a statically indeterminate problem. Okay? Because we cannot solve for the reactions just from the equations of statics. Those of you who are in mechanical or civil engineering, when you go to second year, you will learn how we can solve for this extra unknown using the deflection problem. By accounting for deflection of the beam, we can solve for the extra unknown also. Alright, let's do another example, very interesting example. So think of this frame here, or let's say a network of links. So here is one link, then we have another link, and there's a third link. All right, and then it's pinned. So each of the joints are pins. Okay, each of the joints. So we have A, B, C, D, and E. A, B, C, D, E are all pinned. Alright? And suppose we apply a force here, F. So this is also a coplanar system. Okay? So we can get at most 3 equations. Now let's say I want to get the reaction at the supports A and E. So how to get reaction at support A and E? Alright? So you see at A, because it's a hinge joint, it has at most AX and AY. And then at E, because it's a roller support together with hinge joint, it has at most EY. So we have just 3 reaction support for the entire network of links. And we also have 3 equations, right? So 3 unknowns and 3 equations. Correct? So this can be solved. Let us say we get more Let us say we get more curious and want to know what is the internal reaction at C. Okay, so in that case, what we can do is we simply isolate the link AC. Okay, so let's isolate the link AC. Okay, so we have a point B also here. At C, again it's a hinge joint, so you have CX and also CY. At A, you have AX and AY. But what about B? So if we look at the original picture, BD, look at BD. So if we just draw BD, you can have a force at B in an arbitrary direction, similarly force at D in an arbitrary direction. But you can also recall from previous class, because it's now a two force member, right? It's a two force member. That means the reactions at B and D must be such that they lie on the line joining B and D, isn't it? So this is something that we already learned. So it has to be like this. In fact, you can recall if you have a member like this. So let me redraw. If you have a member like this, and the other two ends, and if it's a two force member, then the force at the two ends has to lie along this dotted line. Then only this member can be in equilibrium, net force being equal to 0 and net moment also being equal to 0. Okay, so coming back to link AC, then at point D, we then know that it has only Bx as the unknown. There is no By present here. Now Ax and Ay have already been obtained, right? So how many more remaining? Bx, Cx and Cy. So again three unknowns. And link AC is a single rigid body. So you can apply now force balance and moment balance, and you get three equations. So force balance and moment balance of link AC gives us the desired three equations. Alright? Let's do another example, which is again a planar example. So we have this setup. So let me redraw. Alright. So you can see we have two links here. The bottom link is subjected to terminal load. This is a hinge joint. This one right here is also a hinge joint, whereas here it's clamped. Again, the question is, can we get the reaction from the supports using the equations for statics? So let's just draw the free body diagram of the entire system together. So we are going to have two reactions here. Let's say AX and AY. And this is the known load P. But over here at the clamp point, we will also have movement. See it? So it is Bx, By, and N. So how many unknowns are present here? So we have total of 1, 2, 3, 4, 5. 5 reactions and 3 equations for the system. Right? As of now, 5 unknowns, which are Ax, Ay, Bx, By, and N. It's called Nb, but only 3 equations because it's planar case, right? Certainly it doesn't seem like we can solve, but maybe let us break it into 2. So let's break it into 2. So we have the first link, and we have Ax, Ay, and over here it's again a hinge joint. So we have, let's say, Cx and Cy. Then for the curve, we have the reactions Cx, Cy, and Bx, By, as well as Mb. Now can it be solved? So here again we have 4 unknowns. And here we have 5. But if you see as a whole, because 2 of them are the same, isn't it? So we have total 7 unknowns. And 3 equations each for the 2 links. So again we can't solve it. So this is again statically indeterminate. Let's change the system slightly. So we again have the same 2 links. But now it is hinge joint even at this end, okay, so all three are hinged. B, this is C, this is A. Now, if you just concentrate on BC, the curved length BC, because of hinge joint, the reaction is just a force, right? B and C. So it's actually a two-force member then, right? There is no moment reaction. So now it's a two-force member. Earlier it was not a two-force member. But we know for two-force member, from its force and moment balance, we know that the two end forces have to pass through the line of action joining the two endpoints. So it simply means we know the direction then of the two forces. Okay? So this makes our life easy. So having known this, then we can come back to the whole system together and at B we know the direction of the force, we just don't know the magnitude, isn't it? So let's call this just B, and at this hinge joint of course we have both components unknown because direction is not known, and now you see it has three unknowns, AX, AY and B, and we also have three equations. So that means this is now statically determinate. Okay, very interesting, isn't it? Okay, let's do one last problem. So this will be a 3D example. Okay, so think of this vertical wall to be horizontal surface. And we have a curved bar, let's say curved beam, spatially curved beam, isn't it? Right. So the two supports here are ball and socket joints. Okay, this is ball and socket joint. This one is also ball and socket joint. Okay, so let's say this A, this is B, this is C, and this point is D. At point D, there is a vertical load acting. Let's say ball is hanging at point D, so then exerts a vertical load, and at point C it is connected through a string, and the string is attached on the vertical wall at point E. Okay, so can we find out what is the tension in the string? Alright, so if we draw the free body diagram for this beam, the curved beam, then because of ball and socket joint, this is going to have all three components, AX, AY, and also AZ. Likewise, at point B, it's going to have BX, BY, and also BZ. At D, we have the known DZ. And at C, is a tension whose direction is known, isn't it? Let's say Tn hat, where n hat is simply the vector CE, right? The position vector of E related to C divided by the magnitude. So how many total unknowns are present here? So 3 over here, 3 over here, and 1 over here. 7 unknowns. You see, because it's a ball and socket joint, there is no reaction moment. 7 unknowns, but how many equations of statics? Only 6. So this is obviously statically indeterminate, right? Statically indeterminate. But let's say I want to know what's the tension in the string. So can we still find the tension in the string? If we find out net external moment on this curved beam about point A, then this has to be 0 from statics, right? Furthermore, if we find out the component of this external moment about point A and dot it with the direction AB, okay? So this you can recall from the definition. This is nothing but the moment along the direction AB. If we call this, let's say, lambda, then this is actually moment along the axis AB, m lambda hat. And this is scalar, right? Because we are talking about moment along an axis. The interesting thing is when you find moment along this axis, then the reactions at A and B, they are all passing through the axis. So they do not exert any moment about the axis. And you only have the moments exerted by the weight at D and the tension at C, isn't it? So we could write that m lambda has no contribution from reaction forces at A and B. So this simply implies that m lambda hat is then the moment due to the tension and due to the weight. Due to tension, this is going to be the position vector or point of application of tension, which is C, related to a point on the axis, let's say A, cross product the tension Tn and dot with the axis lambda. This is the moment due to tension plus the moment due to the body weight. That's simply going to be the position vector of the point of application of body weight, which is D, related to a point on the axis, which is A, cross product the body weight, and that's minus Byj, well actually K, right, the vertical load, and finally dot this with lambda. And this has to be equal to 0. So this simply implies that T is equal to minus of R D with respect to A cross product K hat dot with lambda hat into By, which will be known because we are putting a known weight there, divided by position vector of C relative to A cross product N, and this then is then dotted with lambda. So that's tension. So you can see, although it's a statically indeterminate problem, we can still find tension. So statically indeterminate does not mean we cannot get any of the reaction forces or tension. You can get some of them, not all of them. Okay. Even more interesting, can we know where should the string be attached on the vertical wall so that tension is minimized? You can see the string is attached to point E. So we are talking about point E. Where should point E be? So if you change E, what is it changing? The direction of the tension, right? That's N. So basically, N is the unknown here now. N hat becomes an unknown. You see, in this formula for tension that we just found out, the denominator could also be written as RC related to A You see, it's a scalar triple product, isn't it? So this could be written as lambda hat dot RC related to A cross product N, which is also equal to lambda hat cross product RC related to A dot with N. You see here lambda hat is known, RC related to A is also known, and N is the unknown. So if you want to minimize tensor, the denominator should be maximized. So this has to be maximized. And you see, which is this number here. The only way to maximize is that you put your n hat, the direction n hat, should then be along lambda hat cross product RC related to A. Isn't it very interesting that we now know what's the direction for n hat, which means then we can also find the point E. Also find the coordinate of point E. On the wall. Alright? So I hope you got some idea about equilibrium of rigid bodies, the equations of statics. It has 6 equations in general, but in special cases, not all of them are independent. Then we talked about statically determinate problems, statically indeterminate problems, in the planar case, and finally in the 3D case. Alright? So with this, I'm going to end the class today. Thank you.